Okay, so now we are going to have a lecture by Chiaki Kobayashi from the University of Hertfordshire. And Chiaki is going to talk about chemical evolution of galaxies.
Thank you. Thank you very much for coming, also particularly to the organizer for inviting me to such a beautiful place. I'm enjoying very much so far. So I'm going to talk about the chemical evolution of galaxies. I am happy to take questions during my talk, in particular for clarification, the code, the quantities I'm showing and so on. So please raise a hand. Discussion, however, can be wait until toward the end of talk or even tomorrow round table session. So I'm showing how chemical enrichment can be dramatic following the evolution of galaxies in a cosmological context. I'm going to explain this more toward the end of my talk. Just briefly, our universe started from Big Bang about 14 giga-years ago. At the beginning, so we saw the first light with cosmic microwave background and with satellite mission, WMAP and Planck. After that, there was no stars for a while, so it's called dark ages, and the first star formed. And then we can start seeing the structure formation starts formed into galaxies, and galaxy also grow following the hierarchical clustering of the universe. So from the analysis of this cosmic microwave background, we know the composition of the universe. About 26% is dark matter, 69% is dark energy, and only 5% is a normal matter from which stars, planets, our human being produced. So we are talking about this only small fraction of the universe now. From CMB analysis, we know the initial condition of the universe. So now using a supercomputer, it's possible to calculate, simulate in a computer, the structure formation following gravity and hydrodynamics with a supercomputer and with also numerical method. Problem is, we don't know how stars formed, actually. We may hear more about tomorrow by another lecturer. That is uncertain. After star formation, how stars affect to the surrounding matter, interstellar medium, this is also highly uncertain. This process is called feedback. However, once we form stars, the resultant chemical enrichment is relatively well understood. If formed stars are massive, more than 10 solar mass or so, they explode as quark of supernovae, which produce a lot of alpha element, oxygen, magnesium. In interstellar matter, oxygen is usually well observed. Also a bit of iron peak elements as well. Because they are massive stars, the time scale is million years or so. Low mass star can produce a lot of heavy elements if they are in a good binary system. Explode as type 1a supernova, this channel produce a lot of iron peak elements. But they are low mass star. Also in a binary, the time scale is longer. It's about a giga-year or so. Single low mass star can produce a bit of elements during asymptotic giant branch phase, but the production of elements is limited to carbon, nitrogen, and slow neutron capture elements. So therefore, in a galaxy, not only the total amount of heavy elements, we call it metallicity, but also elemental abundance ratio changes as a function of time. So we can use all of these quantities to constrain the history of the universe, history of the galaxy we are thinking. In the Milky Way, we can do this better thanks to the huge amount of observational data. And this approach is called galactic archaeology. So this chemical evolution galaxy is not driven by chemistry. This is driven by nuclear physics. So this is a chart of nuclei, the stable nuclei, so plotted with this black square. In the diagram on the x-axis, the number of neutrons, and the y-axis, number of protons, and the stable nuclei are here. So you can see at given proton number, there are multiple stable nuclei exist. They are called isotopes. And just to remind you, the total number of nucleons, the mass number, is written top left corner. So in the case of carbon, carbon consists of 6 protons and 6 neutrons, in total 12 nucleons. There are also carbon-13 can be observed in the interstellar medium. So that if you look at this black area, the slope is 1-to-1 at the beginning up to calcium, and then this slope tilt toward lower side, which means these nuclei contain more neutrons than protons. This is why neutron capture process is important to explain the origin of the very heavy elements. The most heaviest one is uranium and thorium in these islands. There are various paths how to pack neutrons in a nuclei, the slow process and also rapid neutron capture process are discussed. Also, the astronomical sites have been debated. I'm going to touch briefly later again. So first, we should know how much elements are produced from what kind of stars. The fate of stars depends on the initial mass at the birth. So I'm talking mainly about the mass in the case of single stars, but if these are stars develop in the binaries, these mass numbers will shift slightly. The low mass stars, stars in general shine thanks to the nuclear energy transforming elements into a heavier elements. Most of the case, it happens for transforming hydrogen into helium. The sun will have a helium flash later and then form a carbon and oxygen white dwarf at the end of their life. Stars are more massive than 8 solar mass or so, the carbon can be ignited near the center, at the center, or slightly off center. And then this central oxygen neon magnesium white dwarf may be formed depending on the mass loss. If stars are more than 9 solar mass or so, neon can be also ignited. And then stars above 10 solar mass or so can form iron core at the end of their life. Iron is one of the most stable elements, therefore it's not easy to synthesize heavier element than iron, but iron instead photo-dissociate that reduce the pressure in the center that's triggered the gravitational collapse. This way, the supernova explosion happened. After that, the remnant neutron star or black hole will be left. During the supernova explosion, more heavier elements is also produced around the iron peak elements. So the very central part, this is called explosive nucleosynthesis, particularly chromium and manganese produce slightly outer area, and zinc and cobalt are produced in the most ejecta of supernovae. What happened to exactly the very central part? How much black hole or neutron star is produced is uncertain. And this, in this kind of 1D calculation, this is treated as a parameter. The central part, just go back to black hole, it's called the fallback. And then slightly surrounding the area will be mixed. Some of them material go to black hole, some of them may be ejected. This mixing area is also given by parameters. There are various groups calculating these nucleosynthesis yields. The 3 major one, US group, Italian group, and our Japanese group have more or less similar results if we look at zero metallicity and typical 20 solar mass of star with a normal explosion energy, 10 to the 51 L, it's called 1014. At metal enhanced stars, the variation becomes larger because of the stellar mass loss. The description depends on the stellar evolution codes. So roughly speaking, I'm plotting now how much elements are produced at each mass of stars on an x-axis. The number is also plotted here, but you see the production element is very slow, small, up to 10 solar mass. And there are a lot of heavy elements are produced after 10 solar mass. If you look at the line, the production of elements, it goes up to the top right, meaning more elements are produced from more massive stars. So if you also look at the oxygen and iron, the slope is different. That meaning oxygen to iron ratio is larger at more massive supernova. This figure looks very different when I extend to the more massive end above 140 solar mass. So such massive stars became unstable during the oxygen burning phase and then suddenly explode as pair instability supernova. So this pair instability supernova do not produce a black hole, so everything explodes. So a lot of iron is produced from this channel. So this is very dramatic. And significant amount of oxygen, and in particular, this green area, a lot of oxygen burning into silicon and sulfur. So this is very strong signature. The observers try to look for the signature of this pair instability supernova, but yet there is no signature found in the Milky Way. So probably in the Milky Way, there is no such massive stars above 140 solar mass or so, and maybe in the past, there was no pair instability supernova in the Milky Way, but maybe different in other galaxies. If stars are more massive than 300 or so, these stars are likely to just collapse into black hole, intermediate mass black holes. They may merge together and will become supermassive black hole by now. That's another story, important for galaxy evolution called AGN feedback from active galactic nuclei. So the supernova, I said the uncertainty is the central part component, how much iron can be ejected from the innermost area to interstellar medium. So supernova, this quantity, the ejected iron mass, can be estimated directly from nearby supernova. So there are various examples of supernova light curve, how much brightness changes as a function of time, days, and also spectral features. By fitting these quantities, the ejected energy and also iron mass can be estimated. Here, the estimated value is plotted as a function of the initial mass of the star. The famous 1987A, the supernova happened in the Magellanic Cloud, has ejected 10 to the 51 ELK, and the progenitor was probably about 20 solar mass or so. Below that, this energy looks constant, but above, you can see the two sequence. One is more massive stars produce a larger amount of energy and iron. And also the another case is probably successful explosion. So upper sequence is called hypernovae, and the lower case is failed supernova. So how much actually stars go into which sequence is uncertain because of the selection bias. Hypernova are bright, so therefore it can be easier to be detected. And failed supernova, if they don't produce any ion, so they can't be detected by observer. So we actually don't know. So in a galactic chemical evolution models, I am assuming some fraction, roughly half of the star above 20 solar mass go to hypernova, and then the rest stays as failed supernova, above 30 solar mass actually. And these 20 to 30, I assume that they explode as a normal supernova. So these numbers are constrained from galactic chemical evolution models in order to match a number of observational results. 10 years ago, it was not possible to see a successful explosion of supernova in a computer, but nowadays, with very advanced calculation of 3D hydro simulations, we can now see this. This is just relatively low mass stars about to explode in a quite inhomogeneous way. We still don't know how this hypernova type event, energetic massive stars can explode. Maybe with the magnetic field and rotation, it may be possible to have this bipolar explosion. And this may also be the site of the rapid neutron capture elements. so far, I'm talking the very simple case of single stars. Two effects can be important. The number one is stellar rotation. In particular, low mass stars, because of the lack of mass loss, the star can contain angular momentum, and therefore the stars, in particular the envelope, can be rotated quite fast. So if that's the case, without on the left normal HR diagram comparing to the case with rotation, the many stars have this very high nitrogen abundance because of this rotational mixing. The other effect is binaries. With a binary interaction, so the mass envelope mass can be also removed more effectively. And in this case, stars, the hot helium core can be exposed. That meaning hot, bright stars can be more visible in the case of binary. This may be also important to analyze, to estimate the IMF or age of stars in high-redshift galaxies. So these effects many people are working on this, but I'm not including these effects so much in the rest of my talk. So let me explain the very classical model of chemical evolution of galaxies called the one-zone models. There are a number of excellent textbooks. I'm listing some of the reference here, and then you can follow the exact equations later if you are interested in. To make the story simple, so this is the one, I'm gonna combine various things in one equation here. Amount of heavy elements in the gas phase in the ISM changes if there is an ejection of heavy elements from stars. But if there is a star formation, this amount will be decreased because metals are locked into stars. If there is an inflow or outflow to the system you are considering, this quantity can also increase or decrease. So there are various versions of chemical evolution models, but basically we are integrating these equations. The first metal ejection term highly depends on nucleosynthesis yield, the quantity I was explaining so far, and also the assumption of initial mass function, how many massive stars, how many supernova you have per star formation. The binary physics is also important, in particular for type 1a supernova. I'm going to tell you more about this. And then most importantly, in the background calculation, nuclear reaction rate. Some are uncertain. Nuclear physicists making a big facility to detect for the experiment to calculate this rate, nuclear reaction rate. Depending on this nuclear reaction rate, stellar evolution can be different. Also, nuclear is also can be different. So this community is called the nuclear astrophysics. So we are talking to the nuclear physicists, stellar evolution, also galactic chemical evolution, and try to understand this, that beginning of the tree component. And I'll be working on my collaborator and also a close friend as well, Amanda Caracas in Australia, and also Maria Lugaro in Hungary now. The last three terms, I call them galactic terms. So these are depends on the galaxy evolution. Ideally, these should be given by dynamics. To do that, we need to have this supercomputer to follow this. So the beginning of the simulation I was showing is using this fully dynamical model for the last three terms. Initial mass function in a galactic chemical evolution, it is defined as the mass fraction of stars in the mass interval m to m plus Tm. It is often approximated with a power law independent of time, so it's just a power law. It is also normalized to unity within the interval from low mass limit and upper limit. In a local universe, it can be estimated from observation by counting the number of stars at a given mass. Salpeter did this a long time ago, and he found the slope is about 1.35. This number can also depend on the environment, which also many people are discussing now. It's important to note that if IMF's defined for the number of stars, this slope is 2.35. So there is one difference here. There are various versions of initial mass function in the community. I'm comparing the popular ones compared to the salpeter. Nowadays, the smaller number of low mass star is preferred by Krupa, also Chabrier, IMF. Even with salpeter, the calculation with salpeter, if people choose a suitable this lower mass limit, actually it's possible to get very similar results as Krupa IMF. What I'm using is Krupa IMF with a 3 broken power law. And the result is very similar to Chabrier IMF. You can see it's very similar. And in a Galaxy simulation, many people use Chabrier IMF. To solve the chemical evolution of galaxies, we have to assume one thing. The interstellar medium in the system we are considering is instantaneously well mixed with a uniform chemical composition. If we do that, we can see the same equation I was showing earlier. The fraction of gas decreased by star formation, increased by ejection from supernova, matter ejection in this case, and then can be increased or decreased by inflow and outflow. Stellar fraction increased by star formation rate, but once supernova occurs, this material go back to the interstellar medium, so it's the negative term of the ejection rates. And the metallicity evolution is the equation I showed already. A star with initial mass m, lifetime tau, remnant mass fraction w was born at t minus tau time and die at t. So if we do that, the ejection term can be calculated. The fraction of 1 minus w is ejected. And this mass of star was formed at the rate back then, t minus tau. And this mass is weighted by initial mass function. Similarly, for the metal production, we have to use the nucleosynthesis in the beginning, the rest is the same. This is not enough for galactic chemical evolution. The most important part is the last one. Some of the metals are in the star already when they are formed and just returned when stars are dying. So we call this unprocessed metals. It's just recyclable matter. So this component is 1 minus, this is remnant mass, black hole, neutron star, white dwarf, and these are processed metals. It's already in the nucleosynthesis E table. Subtract them, and the metallicity, chemical composition back then when they are formed. So T minus tau, star formation rate, and initial mass function. So this last term is very important when you think about this evolution of interstellar medium. Finally, the galactic term. So that in this part, let's take the very simple case. So star formation rate is proportional to the gas fraction, and inflow is exponential, or sometimes people use T times exponential. And outflow is, if it's supernova driven, proportional to the star formation rate. If it's AGN driven, maybe just quenched. Let's assume star formation rate becomes 0 at some given epoch. By assuming so-called instantaneous recycler approximation, there are analytic solutions. It's actually possible to solve the differential equations by assuming these. I highly recommended you to follow this analytic solution. It's very interesting. You can see the textbooks I showed earlier. In the following, however, I'm showing only numerical models. In that case, we do not assume instantaneous recycle approximation. We are following the recycle production in this recyclable elements all the way self-consistently. However, note that in a galaxy evolution simulation, sometimes still they are using this instantaneous recycle approximation. In this case, the chemical abundance will be inaccurate. So just to briefly show you the impact of this inflow in this diagram. So the star formation rate is proportional to the gas fraction. In a closed box model, by definition, the gas fraction is already 1 at the start of the calculation. So once you start the calculation, the star formation rate is very high. And then as you are using the gas, converting gas into stars, the star formation just decreases. In that case, chemical enrichment time scale is very short. You see the rapid rise of metallicity and then truncated, not so much evolution later on. This model has a big problem. So although chemical enrichment time scale is short, the number of metal poor star is larger than observed. So this is called the G dwarf problem. The bottom figure is called metallicity distribution function, MDF. And if people look at this metal poor end, the model overproduces the number of metal poor star. This problem, the observational data plotted here is for the solar neighborhood, but this problem exists in pretty much everywhere in the universe. Bulge, early type galaxies, and also dwarf nearby satellite galaxies as well. So therefore, the in-fall models are usually preferred. It starts slow, while gas accrete, star formation is boosted up gradually. The chemical enrichment time scale is slower than this green line. And this bump is caused by type 1a supernova, and then later on truncated. That feature is the same. It can very much with this observation. If we assume outflow, not only matter, but also heavy elements are also removed from the system. So that metallicity becomes lower, and also in a MDF, the profile is shifted to the left side. So you may see this green line actually may be better to explain this observed point, but that is misleading because in observational data, observation of stars, it's very difficult to estimate all the age of stars. We actually don't know it's 12 giga-year or 9 giga-year. Another point is stars can be migrated. Some of these stars are formed in elsewhere and migrated in the solar neighborhood now. So that's why usually it's okay to ignore this point, and the red line is preferred. Type 1a supernova. So these double peak is also caused by type 1a supernova. Type 1a supernova produces iron. Once it's switched on, suddenly this quantity F over H increase. That's why you see the bump here. There are lots of stories here. I don't have time to touch all of them, but just list some recent reviews here. Tycho and Kepler have observed type 1a supernova. We can see only remnants now. These are detected with X-ray. Beautiful image here. And these are type 1a supernova. These are the supernova without hydrogen line, but it shows strong silicon line. That's an observational definition. The rate of type 1 supernova is 10 times lower than quark-gluon supernova in the model. But type 1 supernova is more luminous, so therefore it actually can be observed more frequently than quark-gluon supernova. 1As are used as a cosmic standard candle in a supernova cosmology. That's confirmed the accelerating expansion of the universe, got Nobel Prize, so it's extremely important. However, we still don't know what are they. The progenitor system of type 1 supernova has been debated already 40 years and still it's not converged yet. All what we know is it is a thermonuclear explosion of white dwarf made of carbon and oxygen. No hydrogen there at the start. And either the system is a single degenerate, one white dwarf and then companion star is a normal star, or two white dwarf, the merging of two white dwarf. So these are called double degenerate scenario. And these two scenarios are fighting really aggressively for half century. Now the battle is shifted slightly. How this explosion, how massive was the explosion? So that's now the discussion point now, whether these are exploded near Chandrasekhar mass or near Chandrasekhar mass is about 1.4 solar mass, or much lower than that, about 1 solar mass or so. It's called subchandra explosion. In the case of single degenerate, the 1A explosion is triggered by the accretion from companion star. So it's natural to explain, there is some critical point, Chandrasekhar mass. When the mass of white dwarf reach Chandrasekhar mass, it explodes. So this Chandrasekhar mass explosion is expected for single degenerate. Double subchandra explosion may also be possible in single degenerate. So it's not one-to-one correlation, but it's preferred. While white dwarf mergers, there are not many white dwarf binary systems with the total mass of Chandrasekhar mass. So often explosion happened with a different mass. Even subchandra explosion should be more dominant. The nucleosynthesis signature is very different between them. And for galactic chemical evolution, one very key element, the manganese, can be enough produced only in Chandra explosion. This is the reason I am using only Chandrasekhar mass explosion, Chandrasekhar yield in the rest of my calculation. You can read about this more in this paper. There are a number of problems for the single degenerate channel, this Chandrasekhar explosion as well. One of them is a companion star is not usually discovered. There is one case though in the bottom, but usually they are not discovered, and so on, various problems. That's why it's not converged yet. In a galactic chemical evolution, it's a standard candle. So it's simple. So if we know the rate of type 1 supernova, the ejection rate is just multiplied by Chandrasekhar mass, 1.4 solar mass. Nucleosynthesis yield, there is some variation depending on the metallicity, but not so much. So we can just multiply to the rate, and we can get this ejection rate. The problem is the rate, how many type 1 supernova occur at given time. This is also called delay time distribution of 1A. In the 80s, Greggio-Lorenzini first included type 1A supernova in a galactic chemical evolution with this equation, and Francesco Matteucci's group also using the same equation. But I didn't like this equation when I was writing thesis, so I changed it. So I'm calculating, I'm simply counting how many primary stars, how many white dwarf I have, and how many suitable secondary star I could have, and I just multiply them. So this is how I am calculating type 1A rate. The results a bit depends on the modeling of this 1A. So type 1N contribution appear in this probably the most important diagram of galactic chemical evolution. It's called alpha 2 ion FeO/H relation. On the x-axis now, we take metallicity. So time roughly goes from left to right. In a simple case, exactly go like this. If you think about inhomogeneous chemical enrichment, time and metallicity is not one-to-one correlation, but let's discuss this later. Y-axis, I'm showing the oxygen to ion ratio. Oxygen is produced from massive stars. So it started from the high value, and then later on, type 1A supernova produce ion. So this line decrease depending on the type 1A model. The beginning of the calculation, by definition, there is no metal. They are called the first star, also called population tree stars. We don't know how they explode yet. We don't see them in any observation. There is a lot of story here, but I'm not going to talk about first stars at all in this lecture. If you are interested in, talk to me later. In any case, we can understand, we can study what are they by using extremely metal poor stars, by definition, FeOH -3, below -3.5. And then by analyzing the elemental abundance of these stars, people are working on the nature of the first stars. The main evolution happens after this. It's extremely metal poor star. These are Loma stars included. They explode as normal core collapse supernova, type 2 supernova, and hypernova as well. And these produce this population 2 halo stars. Observational data, you can see oxygen to iron ratio is roughly constant. And these are mostly enriched by core collapse supernova only. While FeOH -1 also sharply, this quantity decrease as a function of time and metallicity. And these are called the population 1 star, disk population. And this decreasing trend is caused by type 1a supernova. And now by definition, here we are 0, 0. That's by definition the solar abundance. Because of this relation, high alpha and low alpha are used as a proxy of galactic age. But this is not linear relation. All the population actually can cover the wide range of metallicity, while young population also have some trend. Okay, so I'm going to talk about this origin of elements, and then we have a short break after this. So to summarize the origin of elements, I have to tell you more about how elements heavier than iron can be produced. AGB stars are the confirmed site of slow neutron capture elements. We can see some radioactive nuclei exactly forming in AGB stars, so this is confirmed. And that's a beautiful ALMA image with star strain. It's not a point source, it's a beautiful image of AGB stars. Electron capture supernova is a relatively low mass core collapse supernova from 8 to 10 solar mass roughly. And this regime is forming oxygen and magnesium core. They explode not by ion collapse, but by electron capture process. These are probably the Club Nebula happened about 1,000 years ago. And there is a pulsar in the middle. So it's a neutron star forming supernova. So this site was suggested for rapid neutron capture process site, but it's the many theoretical calculation says no, they produce only light element, light neutron capture element around strontium, yttrium, zirconium, and so on. Neutron star merger has been suggested a half century ago as the site of neutron capture elements. So what we want to do is dump lots of neutrons in a nucleus. The obvious place is let's think about a star made of neutron. That's a neutron star. If you have 2 neutron stars and collide them, maybe it's possible to form heavy elements more efficiently. So that was the idea. There was no confirmation until 2017 when the gravitational wave detected a signal from neutron star merger. We now have the signature sign of neutron star black hole merger as well, a couple of them. So this is a confirmed site. How much our process can actually formed in this event is still debated. The last one is hypothetical. So this is a theoretical calculation I was showing earlier. If theorists put a magnetic field and then rotation and let star explode, it's possible to see this bipolar ejection, and this matter can be neutron rich. So that rapid neutron capture process can actually happen in this explosion. So this is called magneto-rotational supernova, and another promising site for the rapid neutron capture elements. In my calculation, I'm assuming about 3% of hypernova actually have this, and very rare, roughly 1 in 1,000 supernova. If only tiny fraction of supernova do this R process, it's actually enough to explain observed amount of R process elements. So the long story packed in one slide here. So I'm gonna summarize the origin of elements in a figure you are familiar with. That's the periodic table from hydrogen to all the way to uranium, the most stable and heaviest element. During the Big Bang, only light elements are produced. Hydrogen, helium, and lithium, that is already covered with black color here. Beryllium, boron, slightly small amount is produced during Big Bang, but that's not enough to explain the current value. And then most of them should be formed by cosmic rays. Now I'm mentioning cosmic rays once in this talk. But the production, this exact size, this nucleus is very uncertain, so it's not included in my model. So that's why nothing here. Elements heavier than that from carbon are produced by stars. Half of them are produced with blue color, that's massive stars. And also green, that's low mass stars, AGBs. So AGB also even more efficient to produce nitrogen. So 75% of nitrogen come from low mass stars. Alpha element, oxygen, magnesium, mostly come from quark supernova. I said already earlier, and the silicon and sulfur as well. On the other hand, type 1a supernova produces mostly ion peak elements around this peak. Manganese is a key element for 1a. Not only these ion peak elements, but also some of these alpha elements, silicon, sulfur, argon can be produced by type 1a supernova. So this is often ignored, but important fact. So in this diagram, in this each little box, I'm showing the time evolution. The left side is time 0 Big Bang, and then the right side is now 13.8 gigayear, and this dotted line showing the solar age about 5 gigayear ago. The horizontal dotted line shows the observed elemental abundance in the solar atmosphere. So my goal is, if I integrate all of this, I would like to go through this crossing point of dotted line. So you can see some of the models are successful. Come on, I don't have enough, but nitrogen goes through, oxygen perfect, iron, and these nickel, manganese, these key elements are perfectly well explained. Some of them you can see this potassium or titanium, these are known problems. The probably nucleosynthesis calculation is not enough detailed, so therefore it's not possible to capture the production side well enough. Beyond the ion peak elements, lighter side can be produced by AGB by slow neutron capture process. This is known. Quite a lot of strontium, yttrium, zirconium is first peak, and also barium, second peak, barium, and so on, mostly produced by this AGB star, and then third peak, lead. While other elements are produced by quark supernova, that include electron capture supernova, magnetorotational supernova as well. So that's why this blue is dominant at uranium because of this, mostly come from a magnetorotation supernova. I said 1 in 1,000 rare supernova, but still it can be a significant amount. Finally, neutron star merger is also included. Some of the elements you can see this magenta part, but not so much. The reason is the rate of neutron star merger is much more lower than this magnetorotation supernova. And also the production, element production amount is also small. So that's why neutron star merger contribution does not appear here. So this was surprising, but this is what we got in this chemical evolution models. Is there any questions so far? Yes?
Thank you. So when you show like an alpha over Fe versus Fe over H plot, is that roughly plotting like the rate of type 1a supernova versus core collapse supernova? Like what does that plot tell you?
Yes, lovely. Yes, as a function of metallicity or time. So at the beginning, type 1, there is no type 1 supernova, so it stays constant. And then once metallicity is enhanced, type 1a supernova rate is as not as high as, but it's comparable to quark supernova rate. So star formation is ongoing. So quark supernova is happening all the way. But it's, as you said, the relative ratio is shown in this quantity. One more question in the back? It's okay.
Why is it that type 1a supernovae are not happening unless they're enriched or it's an unenriched environment?
So the both factors, metallicity and also time scale. So the type 1 supernova, in the case of single degenerate, the companion star is a normal star. It's like one solar mass star. The lifetime is long, giga-year, 10 giga-year. That's the main reason. Another details is to increase the mass of white dwarf, the accretion has to be stabilized, and the metallicity is important to stabilize this accretion. Often accretion overflow into the binary system becomes common envelope phase. So that's another reason in this metallicity dependence.
So on this graph, why the first supernova are faint?
That is why we don't know, but observationally, in an extremely metal poor star, many of them have very high carbon enhancement. It's called the SEMP star, carbon enhanced metal poor star. To explain the signature, carbon to iron is high, that meaning iron should be low. So that observationally, many people now believe the first stars are not so bright, explosion of first stars were not so bright, called the faint supernova. It's faint, not failed. So the small amount of iron is produced. That's why this quantity can move forward. And why this happened in the first supernova is, we don't know. Maybe the structure, the first star, the zero metal star is more compact, so that may be the reason, but there is no explanation for that yet. Yeah.
I was wondering if you can comment on the origin of nitrogen. Especially now, people are finding abundant nitrogen at redshift 11.
Yep. That's exactly I am telling in the last part of my talk, but briefly, the AGB produce 75% by this hydrogen burning. So this is carbon is dredged up, and then using this carbon, the nitrogen is produced. So that's the primary process of AGB star is the majority. On top of that, the massive stars can also have a nitrogen, in particular metal-rich supernova already have carbon, and synthesize it, the nitrogen can be enhanced. This is a secondary process of metal-rich supernova. Finally, the Wolf-Rayet stars, probably rotating massive stars, can also have the primary process of nitrogen production from dredged up carbon. The similar mechanism as AGB stars, but it can happen in a massive star. This plot does not include Wolf-Rayet contribution, and it's still, I can actually reproduce with only supernova and AGB star. But as you said, in high redshift universe, maybe nitrogen may be even more enhanced, that maybe because of Wolf-Rayet star.
Okay, I have a question about initial mass function. So there is this power X, and it was interesting to have your comment. Does that parameter is dependent on some parameters of galaxy, or it is stable, like for all galaxies? We assume that.
I assume it's stable. I assume universal IMF, universal slope, and I don't see a particular problem by comparing with observation. That's all I can say. And many people said try to change it, and then let's see. Metallicity will be different. Also, elemental abundance will also be affected. That's my PhD student is working on now by changing IMF slope.
I just can you go back to the alpha element enhancement plot?
Yeah.
I just have a question. So you've linked the alpha element enhancement to time, and I'm wondering if there's anything else that can contribute to alpha element enhancement being present, or is it just like the contributions from the supernovae?
So this is a relative contribution between core collapse massive star to 1A low mass stars. That depends on the IMF as well. So if IMF slope is flatter, you have more massive stars. So alpha to ion ratio can be higher. So everything can shift upper end. This also depends on the binary fraction, which also assumes the constant everywhere in the universe, but that can also depend on the metallicity and so on. So in that case, this decreasing trend depends on this binary fraction.
Can you please go back to the slide number 10 on remnant mass versus stellar mass?
Number 10. Remnant versus stellar mass. Maybe this one, that one?
Yeah.
Yeah.
So my question is, we can see that iron is produced only from stars with mass more than 150 solar mass, right?
No, a small amount of iron is produced here. With this quantity, it's not so visible, but 0.1 solar mass of iron is produced from quark supernova.
Okay, yes.
Yeah.
Thank you.
And then if you integrate by IMF, the majority is around 20 solar mass.
Okay.
Okay, so maybe one last one because we need to go to the next part.
Just a clarification. What are the AMP stars? Can you say that again? In the time evolution step between faint supernova and supernova 2?
EMP stars, yeah.
Yes.
Extremely metal poor star. So that's observed definition. The definition is F/H is below minus 3.5. By the way, there is a hyper metal poor star below minus 5, very metal poor star below minus 4, and extremely metal poor star is, sorry, I said wrong. Hyper is minus 5, ultra metal poor star, UMP, is minus 4, and extremely metal poor star is minus 3. And very metal poor is minus 2. So that's an observer's definition. Okay, so let's have a couple of minutes break, and then I will move on to more detailed simulation of galaxies together with chemical enrichment in the second part. Okay, so let's move on to more realistic universe where chemical enrichment takes place inhomogeneously. So this sounds hard, but using computer, it's possible to simulate them. So I'm usually very much proud of these results, but in this community, I'm not treating inhomogeneous of ISM so well. So my scale, resolved scale, my inhomogeneous scale is kiloparsec. So it's actually 1,000 times worse than you are calculated. But this is the best we could do by following galaxy evolution in a cosmological context. So there are various types of galaxy modeling. I have been talking about so-called one-zone models. It's also called monolithic model. So that it's just one-dimensional calculation, and the central part is more metal rich, outskirt is metal poor. These kind of things can be done. The galaxy evolve in a different way. So to include this hierarchical clustering of galaxies, the semi-analytic models have been used mainly by Durham and MPA, but also other groups are also working on this. This can treat the evolution of large-scale structure as well, but calculation is not that heavy, so that's the advantage. I am not going to talk about this middle model further in this lecture. The last one is a more detailed one. So it started from the Burkhardt and Hensler in the 80s. They named this chemodynamical simulation. This is actually German-made word, so that the native speaker actually don't like this term, but I like it. So let's call it chemodynamical simulations. There are a number of people working on this, and also the big simulation code, Ramses or Aleppo code, and Gadget as well. I'm using Gadget. So these can, in principle, do this chemodynamical simulation very well. So I said the instantaneous mixing application is assumed for the one-zone model. The middle one, mass assembly history, can be included. And the last one, chemical enrichment takes place now, particle by particle. So as long as I can resolve particle, gas particle in my case, I can trace the chemical enrichment locally. In this way, it's possible to predict internal structure of galaxies like Milky Way, the bulge and halo and disk. Also in other type of galaxies, a spatial distribution element, radial gradient can also be predicted. So that is why I am using these chemodynamical simulations. There are various types of different types as well. So some people try to include this inhomogeneity enrichment stochastically. Or some people just use dynamic calculation from n-body simulation and try to couple chemical evolution model as well. So these are also called chemodynamical simulations, they called. But what I am saying is hydrodynamics is calculated together with chemical enrichment. So what I'm doing here is roughly, so I find the cooling gas in the galaxy. So cooling function depends on the metallicity using this result of mappings and so on. And once I found the cooling gas particle in my case, or mesh in other people's case, let's form star particle. This is a collisionless particle now. And the criteria, I take a very simple one. Let's find a converging flow. And then cooling time scale is short, dynamical time scale is also short. And if I satisfy this criteria, I'm gonna make a new star particle. Because of the numerical resolution, I'm calculating galaxy, so I cannot resolve star by star formation. So this star particle already have 10 to the 5 solar mass of stars. So the individual number of supernova in this star particle is calculated, assuming initial mass function. So here I'm assuming this group IMF, and I'm not changing this IMF for all particles in the galaxy. But of course, this star formation criteria is very simple, and this the criteria with different criteria result in a different enrichment history. Once I stand formed, that is relatively straightforward. So the massive stars are dying, releasing the outer envelopes that produce a bit of thermal energy and also a bit of heavy elements, carbon and nitrogen. And these elements are distributed to the surrounding matter, the interstellar matter. How do they distribute them is a big question. It's called feedback. So I'm taking a very simple case. So let's distribute it in 100% thermal form. And in this case, these radiative energies go away. So it doesn't affect so much. While supernova inject 10 to the 51 erg, so it can have an impact. It can suppress star formation with this heating source. But supernova also produce a heavy element, oxygen and iron. So these are cooling source. So the supernova feedback can have a positive and negative feedback. So that's why we have to have numerical simulation. Then this same star particle evolve to the type 1a phase. And this stage, a lot of iron is produced. This is a big coolant. And the final stage is a remnant. It's made of black hole neutron stars, white dwarf. They don't do anything. It's just a n-body particle. It became just moving around the galaxy. So these metal ejections already trigger the next generation of cooling star formation, and this loop is calculated particle by particle. that's all we need for Milky Way. But for massive galaxies, this is not enough. And many simulation people assume supermassive black hole should be produced by somehow. I am assuming supermassive black hole is formed from the first stars, very massive stars. I said already, if 140 solar mass or more exist, they must explode as pair-cell supernova. But we don't see them. We don't see any signature. Maybe they are just became an intermediate mass black hole. So I'm going to follow this, the growth of this relatively small black hole by accretion to other, by merging with other black hole and also accretion of gas. And then this black hole evolve into supermassive black hole in the center of massive galaxies. Energy is ejected proportional to the accretion rate, and this is the AGN feedback component. I'm not going to talk about more about this, but this is also a very important process, in particular for massive galaxies. Very simple case. Let's just run this calculation in a static dark matter halo with a rotating gas cloud. So you saw the star formation happened on a disk plane with a white particle on the right, and then supernova, individual star produces supernova, and then that's, as a result, this bipolar explosion can happen. This galactic wind can be easily seen in this kind of calculation if the initial mass of the system is less than 10 to the 10 solar mass. Above that, gravitational potential is too large, so this galactic wind does not happen so much. That is why AGN feedback should be included to explain massive galaxy evolution. Let's start from the story of Milky Way. In the Milky Way, we now have beautiful, huge amount of a data set. Gaia is measuring the motion, detailed kinematics, motion of stars, billions of stars, quite accurately. There is another method called astroseismology that can estimate the ages of stars quite well. And then by the follow-up multi-object spectrograph missions can measure elemental abundance of low-mass stars for millions of stars now. Some programs are ongoing, like Apogee and Sloan, or Australian Hermes Galar survey, and these are and Gaia also has a follow-up program, so these data are already available. And in coming years, the William Herschel telescope, the WEAVE, and also the ESO's foremost can increase the number of stars dramatically. And even on a bigger telescope, moons on VLT and Subaru P prime focus spectrograph will do the similar thing with deeper, more fainter stars. So these are all low mass stars, but it's possible to estimate detailed elemental abundance accurately. We can get elemental abundance information up to European quite well, but beyond that is harder to detect gold and uranium. We have to have a UV high resolution spectra. And the survey, we don't have the survey telescope for that yet, but that may be the next future I would like to see. Last year, June, there was a Gaia data release 3. I was expecting to see beautiful kinematics map, but also this metallicity map was very surprising. So they showed Milky Way disk has a red, so high metallicity, while there is a vertical gradient. The halo is more metal poor, also radial gradient as well. So this is pretty similar to what we can see in the simulation as well. But in a Gaia, this is beautiful well. The biology, it looked to me, this is too metal poor, so I don't know what's happening there. But anyway, this looks good. So this includes 500,000 of stars in this data set. This was expected, but even more surprising to me was this Gaia release include elemental abundance as well. So that's the alpha to ion map Gaia produced. The disk plane, alpha to ion is low. So the type 1a supernova is ongoing there. So these stars have low alpha to ion, where there is a strong vertical gradient. Halo stars had only type 2 enrichment. It's a reddish color in above plane. The vertical gradient is weaker. So there is some stripe here. That's an artifact. Don't know what it's called in this paper, but anyway, this beautiful data set available. Not only alpha to ion, some elemental abundance they also released. The quality is debated in comparing to even more higher resolution spectral results, but the number of stars is amazing. So I've been running this zoom in simulation of just focusing the initial condition that will have relatively quiet merging history. So the beginning, you see these small clumps are formed in 100 kiloparsec large scale or small scale as well. And the gas accretion takes place. I'm showing only the stellar component here. There is no disk, but the bulge is formed already redshift beyond 2, and disk component form gradually from inside to outside. That this called inside out growth of galactic disk. And then satellite galaxy keep on accreting because this is CDM initial condition. So the small clumps keep on coming, but there is no major merger. If there is a major merger, I cannot keep this disk structure well enough. There was like a Magellanic Cloud type of minor merger happened a few years ago in this case. So this was showing the stellar luminosity map, but also elemental abundance is all calculated in this RAM. Just one point was not included in one zone calculation, which is the motion of stars. So some stars formed on the disk plane, but they don't stay at the same radius for a long time. Because of the dynamical interaction, some stars move. This process is called migration, and it can be important and discussed a lot in the community. So we now plotted here in the same simulation by analyzed my former postdoc, Fiorenzo Vincenzo, who was Ohio State University before. Anyway, so he analyzed where stars formed on the x-axis and where they are located now in the simulation. So we see 1-to-1 correlation as well. So these stars are on the disk plane. It's just circular orbiting without changing the radius. But we see this trend. So stars formed in a 6 kiloparsec, but located at 8 kiloparsec in the solar neighborhood now. So this is the stellar migration effect. And then on the average, we find it's going outwards. The reason is that in a cosmological picture, the disk was small and disk grow inside out. Following this inside out growth, stars tends to move outwards. In a non-cosmological calculation, stars can go out or in, but in a cosmological one, we see one direction of this migration. That can also change the metallicity gradient of stars as well. So the same map I showed earlier, but with a simulation now. So I'm showing now the same quantity as a function of metallicity, oxygen to ion ratio. So now each particle have a slightly different history. Some of them are formed not in the solar neighborhood, but the inner area. But now I take the star particle in a solar neighborhood ring and then made this frequency distribution. Basic feature is the same. So you see the plateau, mostly enriched by type 2 supernova, and Fe over H -1, there is overall decreasing trend by delayed enrichment by type 1 supernova. The simulation predicted these 2 peaks. One is a slightly higher alpha, the other is low alpha. So I wasn't sure about this back then, but now observational data also showed this similar bimodality. And this alpha to ion bimodality is also discussed a lot in galactic archaeology community. The reason is once type 1a supernova switched on, the ion production of ion is significant. So suddenly go to down there. So this sudden change of ion production, this bimodality is predicted in the simulation. Another thing is some stars have low alpha around this sequence. So these are also locally enriched by type 1a supernova. So this signature can be also seen in this hydro simulation, chemodynamical simulation. So not only alpha to ion, but also other elements can be also predicted. Similarly, I take the high resolution observational data. I don't shift anything here. I'm just going back and forth, and you can see not only the average trend, but also the scatter can be well reproduced between observation and simulation. Some you can see there are more points at low metricity. That's selection bias. So observers are hunting for EMP star, extremely metal star. So there are more stars in the data set, but actually in the universe, these are very rare. The majority of stars are just under subsolar metallicity that we know from metallicity distribution function in the solar neighborhood. Then jump onto an even larger scale. So now I'm simulating the entire cosmological volume, but this movie shows only the central part where the most massive galaxy is produced. So you see this color showing the metallicity. Already the color was red at the beginning in a patchy way. So chemical enrichment was ongoing in a small clump, even this filament, small galaxies formed already, it's enriched there. These are supernova-driven wind from small system. These ejected matter collapse into, accrete onto this central part together with heavy elements produced. So this is kind of a complicated evolution happens. And then in this center of massive galaxies, supermassive black hole is also formed in this run that's triggered AGN-driven wind toward the very end of this calculation. So just to roughly summarize, there is some almost cold flow, accretion of almost primordial gas. And also I say accretion, in this case, chemical enrichment is ongoing, metal enhanced gas accrete onto a massive galaxy. And then there is radial flow. The metallicity is more brings toward the center that can also steepen the metallicity gradient. And then the very central part is most metal rich, supersolar metallicity in a massive galaxy. And this from central part, galactic winds are produced. So this wind material mixed into the outskirts matter as well. So the metallicity is about 1/10 or so. It's get lower by mixing. Inter-circumgalactic medium metallicity can be explained by these winds, intergalactic medium as well. And DLA, we can measure element abundance in details as a line of sight of quasars. And finally, even more massive system intercluster medium contain heavy elements. So these ejected metals are trapped inside a cluster of galaxies. So more metal enhanced system can be seen there. Yeah, many people are working on a similar thing. Roughly speaking, the most massive system have more heavy elements, the most metal rich. This mass metallicity relation is discussed a lot in a galaxy evolution. My PhD student posted her first journal paper 2 days ago on the archive, where you can see the details. So she tested various feedback modeling, thermal feedback, kinetic, stochastic. The eagle is using and mechanical feedback. Illustress is, and also fire is using mechanical feedback. So tested these methods. She showed how mass metallicity relation and evolution of the relation can change. So always you see this top right line. So always most massive system is most metal rich, but this evolution changes depend on the method. So this is a stellar population, but also gas phase as well. The same statement is true. And with gas phase, it's possible to measure metallicity in high redshift galaxies. So we heard about yesterday how difficult this measuring metallicity from emission lines. You have to combine with multiple metal lines to get the more accurate estimate. So it depends on the method. So there is a lot of uncertainty, this observed dotted line. And there is already some tension here. So if you look at this modeling lines is very high compared to this observed low value. So there may be some inconsistency is ongoing here. So this is one of the very highlighted problem in galaxy evolution community. So hydro simulation can also predict the internal distribution of metals. It's a detailed, it's an inhomogeneous metallicity distribution, but to make it simple, let's calculate metallicity radial gradient of stars in this case. And the points are the galaxy in a cosmological run. It has a variation. It's almost a flat gradient to very steep gradient. And this metallicity gradient probably depends on the type of galaxy. Early type galaxies tend to have flat gradient. And then we are comparing to this IFU observation, Atlas 3D observation, and the range is pretty similar. We don't see any environmental dependence, and then manga and other surveys is also discussing how this environmental dependence can be seen in metallicity radial gradient. The stellar gradient, we can predict quite accurately. The gas phase metallicity is harder. We have to wait by star forming particles, so that's the challenging part. But observationally, gas phase is better as its emission line. It's possible to measure at high redshift galaxies. So now KMOS survey measured this metallicity radial gradient of the length galaxy sample, but around redshift 2. Surprisingly, these points are around here, very flat gradient overall. And in many simulations, in particular, chemodynamical simulation predict steeper gradient at higher redshift. And this is very different from what we can see in observation now. Maybe because of resolution of observational sites, so they are not resolving galaxy so well. Sometimes they are just looking at merging galaxies integrated. So that may be the reason that it shows the flat gradient, or the estimate of metallicity is also challenging. So that this is another this debated point now. The last, almost the last plot I would like to discuss is this nitrogen problem. So this is probably the second most important figure of galactic chemical evolution. Let's plot nitrogen to oxygen ratio as a function of oxygen. This you can do for interstellar medium in the simulation as well. So we integrated star-forming gas particles to calculate this quantity. So my former postdoc, Vincenzo, also did this work. And we saw this trend. So at low metallicity, nitrogen to oxygen is low. And at high metallicity, it's increased by AGB and metal enhanced supernova. And the color showing a different redshift. So although this trend exists, we actually don't see so much evolution. And in this paper, we said this relation should be universal. The plateau part, so AGB is already included here. So without the AGB, nitrogen to oxygen ratio go down like this. So if I show the same model with one zone calculation, this line goes like that. But with hydro simulation, AGB enrichment is already ongoing. So that's why we can predict this plateau here. Increasing trend is caused by metallicity dependence of nitrogen yield, both in supernova and AGB stars. There are a chemo survey try to estimate this nitrogen to oxygen ratio at redshift 2. similar, there may be some evolution. So this is another new area people can work in future. So we predicted how carbon, nitrogen, oxygen abundance ratio can change, also can depends on the star formation history. This is cosmological run. We picked up typical case. Galaxy A has more old population, while Galaxy C has a slower star formation history. In this case, all this quantity evolution can be different. If observers can measure all these three quantities accurately, in principle, it's possible to go back to star formation history. So that's we propose now. This extragalactic archaeology can be done by using this CNO abundance, and JWST can measure CNO abundance at once. One more element we just noticed very recently. So this is Max Franco was a postdoc at my university. One day he came to me. I can measure fluorine abundance in a redshift 4 galaxy. Is it any interesting to you? And I said, yes. Let me model that. So this is the starburst galaxy, dust disturbing homing galaxy at redshift 2. It's lensed. But clear, this hydrogen fluorine line is detected with this ALMA. So hydrogen fluorine is made from this chemical network, so it's quite stable. So if he measure this depths of absorption line, it's pretty much all fluorine exists in this industrial medium back then. So this fluorine is a very interesting element, but it's extremely difficult to measure in nearby stars. The observable lines are only in the infrared, and usual like UVS or usual the telescope cannot access. But in a high redshift galaxy, it's very clear. This is very amazing. And then we compared with my chemical evolution models. That's observed point of hydrogen fluorine ratio, a lower limit. And with standard model, it's difficult to explain this high abundance of fluorine back then. It's only 1.4 gigayear after Big Bang, probably only less than gigayear after the onset of star formation. So AGB is a source of fluorine, similar to nitrogen, but not many AGBs there back then. Supernova produced some, but not enough. So our conclusion was Wolf-Rayet stars, rotating massive stars, can produce fluorine most efficiently, and this may be the signature of Wolf-Rayet enrichment. So that was the conclusion. I reported this on the BBC News program as well, and then they highlighted, when you brush your teeth with the toothpaste that contains fluorine. So let's think about the high redshift galaxy now. Last year was amazing. I already said Gaia release was June. I was already very excited during pandemic. Later on, also during pandemic, but on a Christmas day, there was a launch of JWST in 21, and it's last year, July. It's only 1 month after the Gaia excitement, the JWST released this one. The amazing quality of galaxies here. This is imaging. I was not enough excited by this imaging. What I really would like to see is spectroscopic information. I know this JWST null spec can cover key metal lines from redshift up out to 10. So that's the really excitement I really wanted to look for. And now probably the most exciting object I think now we have is this GNZ11. So this was a candidate of one of the most distant galaxies. It's confirmed, not to the most distant. There is another paper, have a slightly higher redshift one, but still it's confirmed redshift 10.6, 430 mega year after the Big Bang. And yet this spectra if you are trained well, you have to say, wow, what is this line up here? So this is nitrogen 4 line. It's very strong. And usually, high-redshift galaxy back then is like that. It's similar shape, but there is nothing here. But the GNZ11 has it. It's already commented earlier. So this has a very high nitrogen to oxygen ratio. Oxygen abundance is not low, it's a subsolar. And then in the plot, nitrogen oxygen ratio is up there. Carbon may be also enhanced, that's uncertain. Compared to the local measurement, it's a plateau and increasing trend. The value is very similar to what I showed with simulation earlier, but GNZ11 is up there. So you can find on the archive now, many people trying to explain it. I am also writing a paper now. Just my explanation is Wolf-Rayet stars. I already see Wolf-Rayet's importance in the ALMA data at redshift 4. So to me, it's natural to expand it. So with a very short phase, when Wolf-Rayet enrichment is dominant, I can get this GNZ11 value just about. That is, it's a bit short, I think, but I think I've done all what I prepared today. So let me summarize. My message here is we have quite good understanding of the origin of elements now. So we can use this knowledge to understand evolution of the universe, formation of galaxies, and then evolution of interstellar medium. There are some remaining problems around titanium, and also origin of gold is still debated, but major elements we can use. In the Milky Way, we have 6-dimensional of kinematics and detailed elemental abundance from multi-object spectrogram surveys, more coming. And these are in a good agreement with chemodynamical simulation that include inhomogeneous enrichment, gas flows, and stellar migration. But detailed comparison is yet to be done. We can use the same approach using elemental abundance to understand galaxies. We can use this the approach also to external galaxies. So it's not possible to measure star by star elemental abundance there, but it is possible to get the spatial distribution by integral field unit spectrograph. And Manga, Khalifa, and Samis are showing already beautiful data set for low redshift, and JWST NASPEC can also have IFU mode as well. So this can be also done. And the results are fairly consistent with cosmological simulation, but there is already tension in the mass metallicity relation, also metallicity radial gradient, and high nitrogen abundance is also pointing out some importance of massive stars. Most of them I summarized just recently in the book chapter that's available on this archive, and you can find most of the reference, also the figures as well in this article. That's all. Thanks very much for listening.
So we have time for questions.
Hey, thanks for the really interesting talk. So I've been wondering, when you mentioned that UV observations are required to, well, to identify or to help with to understand the origin of gold, could you explain how is that, what is the importance of UV observations in that case?
Yeah, so the gold is very difficult to measure because the access line is only in UV 300, below 300. So even UV, that VLT has you probably will have a new UV spectrograph called CUBE, but even though it's harder. So the available data is only with HST, and only 3 metal poor stars have been measured for gold. So that's the statistics we have now. And if you go back to this figure, I didn't explain very much. The gold is here. The observed value is dotted line, and my model is 10 times lower than that. So the model does not produce gold so much, even if I include all of them. Magnetron supernova and neutron star merger are still much lower. So we definitely need more observational point to understand this problem. And gold and platinum as well. So these two elements are accessible currently only with HST, but we need to have bigger UV spectra in space. LUVOIR, for example, that's my future I would like to see.
Awesome, thanks.
So a very nice talk, by the way. So you showed this map from Gaia of metallicity, and there were these two regions of low metallicity. And when I saw that, I couldn't help but think of the Fermi bubbles. And I don't know if you had a thought about that, if you can already exclude this, or if it's just completely out of context to think about this.
So these maps you're talking?
Yes, this one.
Yeah, so since I have time, I can show you what my simulation is doing. So my simulation can predict like this. So the metallicity is most enhanced on the disk plane and the bulge. I don't see any blue component around here. Alpha to ion also, low alpha on the disk plane, that's consistent, and vertical gradient. This is pretty well, but I don't, maybe because of this bar. So in this simulation, the bar triggered star formation. So along the bar, type 1a supernova enrichment is ongoing, and I actually see low alpha component. Because of the projection, I don't see so much in this metallicity map, but that may be some feedback from the galactic bulge or some help with bar interaction. There may be something ongoing, but I actually don't know. And on Gaia, the central part is harder to measure anyway, so there may be some observational issue as well. There are high resolution, much higher resolution than Gaia, high resolution spectroscopic survey of galactic bulge stars, and they don't see this low metal component. So this may be a Gaia issue, but we need infrared Gaia. So that's the next thing I would like to see future. Infrared Gaia can look through galactic bulge and get kinematics distance more accurately. That will help this understand this.
Great talk. So how do you define Wolf-Rayet stars, and how is possible to distinguish between high mass stars or fast rotators?
Yeah, so my definition was theoretical one. So the rotating massive stars that produce nitrogen, CN, and fluorine. So those I call the Wolf-Rayet. But observationally, Wolf-Rayet stars have various phases. Some are nitrogen rich, some are not. So when I say Wolf-Rayet in this talk, it was rotating massive star, the fast rotator. And that's the way to mix in the carbon and synthesize nitrogen.
Great talk. Can we go back to the plot where we saw like compare the metallicity of nitrogen and oxygen to ion?
Yeah, the Alex Cameron one, I think.
Yes, I think is slide 71. Oh, not that one.
Not this one. That one.
The one before.
One before.
Maybe more. Oh yes, this.
Maybe that one.
Yeah, this one.
Yep.
I noticed that there's for a redshift, for the higher redshift, especially like the ones that are between like redshift 2 to 3, there's a the deviation of there's a greater spread in terms of populations for both metallicity in nitrogen and oxygen. So I was wondering like what is the cause of those spread?
Yeah, I guess you are talking about here.
Yeah, I'm just yeah.
So these are these are various things. So you can find various figures in this paper, but also depend on the mass of galaxy, and also partly the mass metallicity relation of galaxy, but also mass metallicity radial gradient also goes to here as well. So some area just contain more AGB enrichment or metallicity. So this metallicity from stars, nitrogen is enhanced at higher metallicity. But where this enrichment becomes dominant depends on the galaxy formation history. And probably because of this small difference in the star formation history, we see more points around here. Another explanation is the dilution. So this galaxy is enriched from the same ejector here, but with accretion of hydrogen, this point is temporarily moved to this left side. So that's another explanation. We haven't analyzed in this details yet.
I guess I have like a two-part question. So the first part is you talked about radial migration of stars, which is like explained pretty well by the inside out growth of galaxies. But is there like, have you also noticed like radial migration like in the vertical direction for stars, like away from the disk plane, like into higher Z? And the second part is like since these are like, I guess like cosmological volume simulations, you do include satellite galaxy mergers. Like how do accreting like low metallicity halos change the metallicity gradient?
So satellite galaxy is responsible to 1/3 of thick disk components. So they are located in the same disk area, but have hotter kinematics. So temporarily they move away from the disk plane and come back. So these stars are likely to be already formed in a satellite galaxy and then accreted. So that's also exactly where we can see in the Gaia data as well. So that is happening in this Milky Way RAM. Depends on the merging history. Of course, we can constrain how merging history of Milky Way should be quiet or more active. But this is only one set of initial conditions we have run in details. And then the next step is we would like to run similar one with different initial conditions and try to answer your question, how this merging history can be identified from this comparison to chemical abundance.
Thanks for the talk. It's a bit of a naive question, though. I remember when you were talking about the thermodynamical simulations, you assumed that the black holes form from stars way back in the early stages of universal, the evolution of the universe. And much earlier, you made reference to failed supernova. I assume that failed supernova would probably become black holes. It's time to be corrected there. But I keep wondering whether there's at all a role in which maybe in any of your modeling, do you consider failed supernova and how that affects the overall enrichment or chemical enrichment of galaxies? If you can maybe comment on that a bit.
So more massive stars produce more elements, but with IMF assumptions, the dominant enrichment mass is about around 20 solar mass. So 20 solar mass will explode. They still have a 5 solar mass of black hole after the explosion, but that is included already here. So the majority may be okay here. But if the initial mass function is different back then in the first star, the story may be different. So initial rise of very metal enrichment at high redshift may be affected by these assumptions of black hole formation.
Thank you so much for this exciting talk. I just wonder about when you calculate the metallicity, how do you count for the collapse supernova and type 1a supernova? What's the ratio you set? And is that universal? Because when I read the literature, it can be different for different galaxies.
Yeah, so I'm using exactly the same equation in this hydro simulation, exactly the same as one zone model I explained earlier. So the number of collapse supernova is just based on lifetime of massive stars, assuming initial mass function. The rate of type 1a is a binary equation I showed. I'm counting the number of primary star, number of secondary star, and multiply each other, depends on the metallicity. So the rate between core collapse and 1A depends on time and metallicity, as you saw in alpha 2 ion diagram. So the same thing is also included in this hydro calculation.
So you mean it's evolving and it
Yep, it's evolving as a function of time and location, depends on the metallicity.
So if now we observe spinal elements, do we have like a ratio that we can use? Or
So observers can get integrated core collapse supernova rates as a function of mass. They can do also 1A rate. And these are roughly consistent with what I get after this integrate. But the chemical enrichment takes place particle by particle. So each particle at the beginning phase, they have only core collapse, 100% core collapse. And then these particles move inside the galaxy. The same particle switch to type 1A phase, and this particle producing type 1A supernova only.
okay, thank you.
Regarding this map of Milky Way showing the metal abundances, why are alpha elements more easily removed from the disk than the iron?
So this map is the other way around. So iron is enriched on the disk plane. So star formation takes place longer on the disk plane. So type 1A supernova happens 1 gigayear after the onset of star formation, and star formation is still ongoing. So these stars can be enriched by type 1A supernova, while in the halo, star formation is like burst. The first generation of stars produced core collapse supernova, and the star formation is still ongoing. So they have this high alpha population, but that's it. And the type 1A supernova is probably occurring in the outskirts of galaxy, but no stars are formed, no new stars are formed. So that's why you don't see ion contribution from 1A in a halo and also the outer disk as well. So this is a star forming, it's not the ISMN. So if you're thinking about the ISMN metallicity, if star formation is 1A is happening in outskirts, you should see ion in your ISM, but this product is stars. You have to have production and star formation to see this.
Okay, so I think we can thank Chiaki again.